Well, thank you for the kind introduction. I just also want to offer my thanks to Jay Precourt for his hospitality and leadership, and all the people in the backstage. They're working so hard. They make all of us look good. I just want to thank all the organizers out here. So there's been a lot of talk about oil and gas, and I thought I'll just maybe change the topic a little bit and talk about the grid. The grid is really the lifeline of our nation. Without the grid, we would be back in the 19th century. And without grid, there would be no Google. Let's just be frank. So this is considered, let me see if this works. Is there a better clicker? Okay. The US National Academy of Engineering came out and said this is the greatest engineering achievement of the 20th century. And they're absolutely right, because this is a baseline infrastructure that was created in the 20th century upon which we have other infrastructures now being built up. Oh, thank you. So I want to give you talk about three topics. The current paradigm of the grid. And this is, while I'll talk about the technology, it's more than the technology. There is the market structure, the institutions that have been created to enable the technology to be brought to the people. There are some worrisome trends that I'll talk about, and a shifting paradigm that Secretary Schultz alluded to yesterday. So let's talk about the current paradigm. What is the paradigm? The paradigm is the following. You have centralized power generation, which are many a times away from the population centers. You have high voltage, long distance transmission to where the people are. Then you drop down in voltage using these transformers into the distribution network, and then you get feeder lines along your neighborhood at 13 kilovolts, which get dropped down to about 240 volts and come to your home, half of that, 120 volts. That's how it works. This paradigm goes back to Tesla and Edison. The architecture of our grid goes back to, it's 100 years old. The architecture has not changed. The devices have changed. And it's a one-way flow with centralized generation. Why centralized? Because it was cheaper. Because there was economies of scale to generate electricity at large power plants. And then you distribute it to multiple loads. That's the paradigm. And to enable this paradigm, institutions have been created and business models have been created. I just want to touch a little bit on that. This could be 3-quarter or year-long courses in Stanford. And I'll try to make it as simple as I can from what I understand and distill it down to what has been done. This has led to, of course, the blood vessels. These are the equivalent of blood vessels in the United States, the long transmission lines. And then, of course, there are capillaries, which are the distribution network. That's what this is now, because of this, the United States runs. So if you look at this, what is the paradigm? There is, and I'll take California as an example. And you could take many examples, but let's just take, I'm a little parochial on this. There's the high voltage wholesale market. And this is run by the California Independent System Operator, ISO. And they manage the wholesale market side of it. And the markets are important. And they're regulated by FERC and NERC. There are lots of acronyms. But this is the federal level of regulation because you exchange electricity between states. And so you have to have federal regulations and rules that are made by NERC. So in this high voltage transmission, people feed in electricity and people withdraw electricity. And these could be solar plants, could be wind plants, could be natural gas plants, and could be utilities, which have their own plants. PG&E, Southern California Edison, San Diego Gas and Electric, SMUD, which is a municipality, and many, many more. So that is now, these are regions now. PG&E has its region. There are monopolies out there. They're regulated monopolies. But they feed into this Cal ISO, which is a wholesale market, which is not-for-profit organization. And then the PG&E, let's say, which is where I am from, They withdraw electricity, and they can dump electricity to the wholesale market. They can buy and sell, but they also feed the load centers, which is where typically homes and buildings and factories. And that part is regulated not by the federal level, because it's state-wise, by the Public Utility Commission, in this case, the California Public Utility Commission, and that goes as the retail market. So we have created, based on this paradigm, the technological paradigm, we have created markets, and we have created institutions to manage that. And it's very important that we recognize that it's not just technology, it is the holistic view of things. So how does the wholesale market run? Well, this is how it runs. You have all these people, all the generators, bidding for markets, but it's not like a stock market. The stock market is real time. Because we don't have information flowing on real time, what we do today is what is called the day-ahead market. So most of the electricity that we're getting here in Colorado, the load was predicted yesterday. And it's not real time. But then we don't quite get it right. There's a little bit of a gap in our prediction. So then there is an hour-ahead market. Well, that's a little tweak. That's a little smaller knob. And then the hour-ahead market doesn't quite get it right. There's a 15-minute market. There's a 10-minute market. And then there's a frequency regulation, which is real time, which is a very, very small fraction of the whole load. That's how it runs. And if you go to the Cal ISO in Folsom, you'll see all these panels, and there are people trying to manage and keep the frequency at 60 hertz plus minus 0.06 hertz. That's the game they're playing. It's amazing. So that's how the system operators work. And this is a typical day. I picked up Jan 13th. This is on my way to Stanford to give a talk on this. And so this is a typical day. And as you can see, the day-ahead market is the purple line, and the actual demand is a little bit different at certain parts of the day. In fact, it could be on the order of a gigawatt. And we don't have storage. So that's why you have the hour-ahead market, and then the 15-minute market, 5-minute market, et cetera, to get it right so that the frequency does not deviate too much. And you can see at the bottom is the generation, the renewable generation. And you can see the solar peak that comes. In fact, solar is more predictable than wind, because you know when the sun rises, when it sets. And if you are in the desert, there are generally not too many clouds. So it's very predictable. And you've got wind and geothermal biomass, et cetera. So that's how, this is the data from a typical day from ISO. And I want you to note the flatness between noon and then there's about 6 o'clock, there's a little bit of a peak that happens when people go home. And I'll come back to that later on. So how does the utilities run? So PG&E, I'm in the PG&E sector. The pricing, the markets in PG&E are very different in the utility sector. And this is the rate structure I have. I have tier 1 rate. If I only use so much kilowatt hours in a month, I pay 13 cents a kilowatt hour. If I go a little bit more, I pay 15 cents. And then it jumps to 32 cents a kilowatt hour. And I have no idea when I'm crossing. That's the state of the art today. And if I try to explain the pricing, the tier structure to my mother, she's not going to understand this. But that's the nature of the game today. And most people don't understand what is kilowatt hours, the dollars per kilowatt hours. And that's why there's a blindness associated with this. And I think it's really important to get transparent in a way that people can understand. And I'll come back to that later. There's some worrisome trends. We talk about global warming and climate change. And we talk about the fact that the world has warmed by 0.8 degrees from the beginning of the Industrial Revolution, when the United States was being created, 1776. That's around the time the Industrial Revolution was starting. So 0.8 degrees is the average that has gone up. And people are worried about 2 degrees, et cetera. What people don't often talk about is not the average, but the distribution about the average. These things move around. And I'm going to show you a movie of the deviation from the average and plot it as a bell curve. And I'll see this bell curve move over time, normalized by the standard deviation. So here we go. Here's the bell curve. This is the theory. The blue is the cold, when it's colder than the average, and red is the hotter than the average. So the 1960s and 70s. This is the 80s now. This is the data. you can come to your own conclusion which way things are going. And while we do not understand the impact of these heat waves, so let me show you the geographical map where things are. So the average has certainly moved, the distribution has broadened, and the tails of the distribution have a disproportionate effect on our systems, on our grid, than the average. And we should really understand that and pay attention to that. This is how the geographical distribution looks like. And this is a little messy, but the top row is in 1955, 1965, and 1975. Yes, there were heat waves. But this is on the second row is 2006, 2007, 2008, then 2009, 2010, 2011. And as you can see, yes, things are a little browner than the top row, and the hot spots keep moving around. It's not at the same location. So we had a really hot summer in 2012 in the United States, but 2013 was not so bad. But it's like a bubble in a carpet. You know, it goes away out here, it shows up somewhere else. And, you know, the whole world, we are in one world. And somewhere or the other, it's showing up. We understand global warming. We do not understand climate change. And if we understood, we would be able to predict all this. But we don't yet. This has impact. When you have a heat wave, the electricity system is really stressed because you need power for air conditioning or other things that are going on. And I just want to show you, this is the weather, the outages that we have in the United States on a grid. We do have outages. And it's about $100 billion per year loss. There was a White House report that just came out. And the weather-related ones, about $30 to $40 billion, this is not going down. This is only going up. And so this is a trend. This is a really worrisome trend. The other trend is the age. We have $1 trillion of assets on our grid today. And this is one asset. This is the substation transformer. The expected lifespan of these transformers is 40 years. And guess what the average age of the transformer in the United States is? It's 42 years. So we are -2 in life, expected life more. This is where we are. The other one is cyber-physical security. And Secretary Schultz mentioned a little bit about an incident. I just want to give you a little more detail on that. This happened on Highway 101, just in the middle of south of San Jose, north of Morgan Hill. It's called the Metcalf, PG&E Metcalf substation, 600 kilovolt. A lot of transmission lines come there and then go into the San Jose area. So this happened, those transformers that I mentioned, they are cooled by mineral oil, and they're radiators that dissipate the heat away. And at 2 a.m. on April 16th, a few gunmen shot 120 shots at the radiators, exactly, they knew exactly where to shoot, to leak out 50,000 gallons of oil, the 10 transformers that they hit. And 15 minutes before that, they went to the level 3 vault of the fiber optic cable and telephone lines, and they sheared them. So the 911 was disabled. So this is not just a physical attack, it was a combination of that. And for a long time, no one heard about it. In the area that we live in, we live around here. We didn't hear about it. Why? Because this happened within less than 24 hours after the Boston Marathon bombing, where all the media was focused over there. Frankly, I don't want to see a trend in this. This is not something we want to see a trend on. We need to stop this right away, and we still have not figured out who did this. That's where we are today. This is a worrisome trend, worrisome fact. I don't want a trend on this one. The load curve that I was talking about is the following. This is a typical load curve. It flattens out between noon and 4 p.m., and then 4 p.m. to 6 p.m. it sort of rises, then it goes down. This is a typical California load. This is what is going on right now, and this is where the future is going to be. This load curve is going to go down between noon and 4 p.m. and then go sharply up between 4 and 6 p.m. And this is what is happening. This is called the duck's belly. It looks like a duck, and the duck is getting fatter. All right? And this ramp rate is about 150 to 200 megawatts per minute. This is amazing. And the ISO has to balance the grid. The utilities don't. And this is a real problem that they have. Why is the load going down between 12 and 4? And that is because we have solar panels on rooftops, which provides a negative load. And this is a problem of stability in the grid. So what is the ISO trying to do? Well, they don't have too many knobs to run. In fact, they're thinking of negative pricing between 12 and 4 so that they'll have to pay someone to take that excess electricity away and then suddenly ramp up those gas turbines between 4 and 6 p.m. to get that 150 to 200 megawatts a minute. It's a pretty crazy time. And we don't have storage to do that. And so this is where we are. This is a trend which is not a good sign because it leads to instability in the grid. So let me talk a little bit about the good news part, the shifting paradigm out here. First is, here's what's going on. And this is a chart from our Secretary of Energy about solar. This is the US PV module cost and the blue, the bars out there. And it has, as we all know, it has come down substantially. And the deployment of US solar has gone up in an exponential way. And this is the panel cost. It's less than $1 per watt. It's about 65 cents a watt per watt. But this is the fully installed cost, which really is what matters. And as you can find, the utility cost and the fully installed residential cost is higher, of course, than the panel cost. But the most of the cost is not in the panel. It's in the installation, permitting, et cetera. And that will come down. That means there's room for improvement out there. But as a result of these trends, here's what is going on. You can see the retail electricity price, which is the New York grid, the California grid, the Hawaii grid is way up there, and the average US grid. And you can see this purple line of the cost of producing electricity from solar at the residential level, and that's coming down. And when that crosses over, people will realize it'll be cheaper for me to get financing so that I don't have to pay anything upfront, put solar panels on top, and it'll be cheaper than buying electricity from the grid. That's obvious. Storage costs are going down. Okay, this is lithium-ion battery cost, and when we were in ARPA-E, and Dave Danielson ran a program on grid-level storage, and that led to another program on grid-level storage. And I just want to give you a few examples. This was the goal on grid-level storage, that we need to develop technologies and focus innovation on reducing the cost. And the capital cost, the bar, was $100 a kilowatt hour. Why? Because then the levelized cost of storage would be only 2 to 2.5 cents a kilowatt hour. And the only way that has been done today is by pumped hydro. Pumped hydro is about $100 a kilowatt hour. You say, that's the bar. Engineers have to figure this out now. And we wanted all the other technologies to get down to that level so that they would be competitive without subsidies. That's the right way to do it in a sustainable way. And out of that innovation, there are a lot of things that are coming out now. City College is developing a zinc manganese oxide battery. They're transitioned to something called Urban Electric Power, which is a startup company. Arizona State University, Cody Friesen, has developed a zinc air rechargeable battery. They have got Fluidic Energy as the company. They're piloting things overseas now, and they're monitoring everything. This is in the pilot stage. Primus Power, which is a zinc-based battery in the Bay Area, they're developing grid-level storage, as well as something coming out from MIT, which is a lithium-ion battery with a completely different architecture of a flow battery. And that's a startup company called 24M. These are all in the stages of piloting these technologies to see how they run. They're not at $100 a kilowatt hour, but once they start piloting, once they get to scale, they will come down along that learning curve or the Moore's law for batteries. So this is what is going on. This is pretty good sign. Electronic power conversion. This was the way to do power conversion for the last 100 years. These substation transformers are about 8,000 pounds. They run at 60 hertz. You need a crane to install. And by the way, we have a backlog. There's a stockpiling going on of these transformers because the backlog is about 6 to 24 months. So we don't just have a nuclear stockpile, we have a transformer stockpile in the United States. So we thought about this and said, could we do something better? Could we use modern electronics to do conversion, AC to DC, or go up and go down in voltage? And out of that came out a program called Power Electronics using different kind of semiconductors than silicon. Silicon is not the best. This is silicon carbide. This is a single transistor that can handle 15 kilovolts, run 200 amps, and that's, or 100 amps. It's 1.5 megawatts of power going through a single transistor. You start putting this transistor in circuits, and you can do AC to DC, DC to DC, and go up and go down in voltage, these solid-state transformers. And if you could do that not at 60 Hz, they operate at 50 kilohertz, that 8,000 pound transformer goes down to 100 pounds. You can put it in a suitcase and take it with you. And why silicon carbide? Because the United States is the biggest manufacturer of silicon carbide in the world. So it was our strategic interest to focus on this material, and I'm glad to see the president go down to North Carolina and start a manufacturing center on silicon carbide-based power electronics. That is our strategic strength in the United States. And finally, we have put measurement units. We did not have measurement units called phasor measurement units along a transmission system. All the blood vessels that I showed you, we really did not know what was going on. So these are sensors out there that can measure voltage, frequency, phase angle, current, and with GPS location every 30 milliseconds and send out the data. We're getting petascales of data now. We don't know what to do with it. That's where we are. But there's an opportunity out here. I want to transition to this paradigm shift. Where does all this fit in? But this is the current paradigm, and has been so for the last 100 years. We have wholesale market giving electricity to the utility in a one-way traffic to the home. The wholesale market is not a real time. It's that, as I said, day ahead, hour ahead market. And then we have this rate structure, which even I can't understand fully. Okay? So this is where we are. And let me show you what it should be. Let me tell you, given all the trends that we're seeing, where this could go. Here's what it could be. A shifting paradigm. You certainly need the wholesale electricity. You do need electric utilities, but it doesn't need to be a one-way. Why? Because you could put your solar panel on your home. And if you really want to, you should be able to turn it off, but the utility should not get hurt by it. You can have a Nissan. I have a Nissan Leaf. I drive this. I charge it. It's actually cheaper for me to do so than run my gasoline car, the amount of drive. You can have home-level batteries. You can have a gas utility, and could be the same utility, by the way. Gas is coming to your home. You can run a generator to run your electricity. But the waste heat from the gas could be used to heat up your water. It's great utilization of our natural resources. Why is this not happening? The gap out here is information. When I plug in something let's say I take a water heater or my hairdryer and plug it in, the ISO really does not know I plugged it in. But if I take a USB stick and plug it into my computer, the computer immediately recognizes that this is a device, I should do something with it. So that is information flow. And all the information that we're getting at the ISO level, if I can plug it in, I should be able to respond to a problem. The duck's belly problem that is going on in the ISO level, they're really hurting. Why can't I take my load at my home and be able to take some of that electricity and charge my batteries? That communication link is missing. So there's a big challenge in the information flow all through. And we're living in Silicon Valley, the home of information technology. And if you could do that, then what information would you pass through? Well, dynamic prices. Why do you have this tier structure? If the price is going up, that means the demand is high. Maybe the demand should be lowered, so increase the prices, the demand would go down, just like a stock market. Could we have information of the dynamic demand and supply? If a wind is coming up, right now it's ramping up, well, maybe I should charge my water heater with electricity. That information should be there so that I can balance out. The generator doesn't have to always follow when I switch on the light. The load can follow the generator, which is a shifting paradigm. So now the question is, okay, how do we do it? I think at the end of the day, this is my personal belief, we should focus on the people. So what does the person want in this grid? The consumer wants certainty. And I think Secretary Schultz mentioned security. And I like to, this is what FedEx, Dennis Beal said that yesterday, certainty. Let's make certainty of electricity under all circumstances. Whether it's Katrina or Sandy, it doesn't matter. I want certainty electricity. Lower cost, everyone wants that. And environmentally clean, no one wants a dirty electricity. This is what the consumer wants. There's a lot of questions going on in the industry right now. Will the utility model change? There's a fight going on between the solar deployment people, solar cities, and the and the utilities. I think that's a waste of time, frankly, because there's a partnership out here that could be profitable to both. So the question comes up, and I'm not a policy wonk, I'm not going to give you ideas on policy. I like to give you how I think about it. What about the utility policy? And go back to the quote by Henry Ford. It's not the employer who pays the wages. The employees only handle the money. It is the customer who pays the wages. So focus on the customer and see what they want. Give them options. When I'm at home today, I have a telephone line, I have a cable company, I have satellite for my TV, and I have cell phone coverage. And I have a device which integrates, and if something goes down, I can run the other. I have options. And I think this is what we should be looking at if there is a utility policy, to give options to people and figure out a way to make money. The question is the technology, what about the technology? And this is where I think this is the challenge for the engineers. And I just want to end with a quote that we need advances in technology. And this is a quote by Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic. And I think this is the role of the engineers to create some magic, and I think they can if the right market and policy structure is there. Thank you very much. Let me take some questions.
Yeah, let's go over there, and maybe we'll sit down and. Yeah. Okay, great. Well, thank you very much. Okay, well, we already have some questions, so I think I'll just dive right in. This one might be a little hard. If you think you shouldn't answer it, don't. So how does Google plan to minimize the cost of increasing electricity demand for future data warehouse cooling and storage via technological efficiencies and renewable resources?
Very simple. Not a difficult question. Google is a 100% carbon neutral company. So how do we get there? Number one, make the data centers as efficiently as possible. So there's something called a PUE, the power utilization effectiveness. And that number in the industry used to be 2, which means for every unit of electricity that you use for computing, you needed another unit of electricity to cool the computers. And we have now reduced it down to 1.05 or 1.06. And that means we only use 5% electricity to manage everything. So that reduces the burden on electricity demand. But not to say we're not going to build more computers. Yes, we will. That's one. We have worked with Duke Energy, and this is where the partnership comes. And we created what is called the green tariff structure. That means we are willing to pay more for wind and solar and renewable electricity but we want more integration on the grid. So we create a different tariff structure for that. And then what we cannot offset, we just buy carbon offsets. We pay. And right now we can afford to do that. So that's how we address climate issues or demands of electricity.
Okay, great. Okay, another question, really building off what you were talking about with storage. Apparently there's a report from RMI with Homer that suggests that solar plus battery systems could reach grid parity sooner than most people think, and especially in areas with high cost. How do you important see solar plus battery systems, and how big of a problem is this going to be for the utilities?
Well, I mean, I think I showed the data. I think people can come to their own conclusions. I think in places like Hawaii, where the price of electricity is 35, 50 cents a kilowatt hour, it already makes sense. I think if you put solar plus storage together, I think it'll take a few years in California, but it's hard to say exactly when. I think we can only see the trend lines and say that, well, I think it's in the next decade, there's a pretty high likelihood that's going to happen. And in the big scheme of things, we're talking about 100-year infrastructure. 10 years is not much. And I think that's, for our children and grandchildren, they will have probably a world where solar plus battery is going to be cheaper than utility electricity.
Okay, so a question for you about rooftop versus utility scale renewables. It looked like your cost of solar, utility scale solar, was considerably lower than rooftop systems. Is that difference going to go away, which will help further promote distributed generation, or do you see that gulf, maintaining that big price differential? And from a sort of efficient utilization of resources from a societal perspective, what's your sense of what the appropriate balance between utility and rooftop solar would be?
I think utility solar will always be cheaper than rooftop solar. It's just the nature of the game of installation, et cetera. You get economies. There is economies of scale out there. See, in the power plant, the economy of scale came from efficiency. The efficiency of a solar panel in a utility scale or at home is not that different. But it's the installation of the balance of system cost that could be reduced at the utility scale. So I think that's where it really matters. Look, I think we should not think that the grid will go away, that we'll be all off-grid. No, that's not the world I think it's going to happen. We need utility-scale solar. We need utility-scale natural gas, electricity. There will be wholesale markets. There will be. The question is, with the shifting paradigm, how do you create the institutional and the legal structure for both to play, and the business model for both to play? And I don't think we have the answer yet, but I think fighting doesn't help.
Right. Yeah.
We need to look at this partnership and enable people to make money.
Yeah. Okay. All right. Great. Well, our sign is flashing, so it's time to move on. So thank you very much. That was fantastic.